let's look at some types of metal alloys. We're going to, what I'm going to do is introduce you to metal alloys and then discuss the types of ferrous alloys. And if you already sort of have a little bit of understanding of metal alloys, you'll understand that there's also non-ferrous alloys, but I will get into that. So let's look into it. This is the entire classification scheme of metal alloys. So this is the pathway. Yeah, it is rushed. It is definitely rushed, but the information is there. Alright, so the main microstructure characteristics in steels, this is the first thing I'm going to mention because it's important, are ferrite and cementite. Now ferrite is soft and ductile and cementite is hard and brittle, and a combination of these two is called pearlite. So why do we need alloys? Combining alloys gives us two advantages. We can enhance the property of a material and we can create new properties from a material, something like that. Types of metal alloys. We can group metal alloys in terms of ferrous and non-ferrous. Ferrous alloys contain iron, and non-ferrous are all alloys which don't contain iron. And we'll approach this topic in another video. So why do we specifically dichotomize metal alloys according to whether they have iron or not? So iron-containing compounds exist in abundance within the Earth's crust. Metallic iron and steel alloys may be produced using relatively economic extraction, refining, alloy, and fabrication techniques. Ferrous alloys are extremely versatile, which means that they can be tailored to have a wide range of mechanical and physical properties. So that's why we usually categorize things if they have iron or not, because it's the most abundant, it's the cheapest, and it's the easiest to use. So the problem is that they corrode, and that's pretty much it. Okay, so this is what we're going to have a look at. We're going to have a look at steels and cast irons, the differences between them. So let's get into it. So steels are iron-carbon alloys, and they may contain traces of other elements. So what effect does increasing carbon? So what I should have said is that steel and cast irons are both made of iron and carbon. It's just that cast iron has, I think, over 1.2% total carbon weight. And what effect this has on increasing the carbon content is that it has increased strength and hardness, but it does become more brittle and it's less ductile and it's less tough. So low carbon steels. And this is the first steel we're going to look at. So this steel is produced in the largest quantity. It's also the least expensive to produce. Well, that's why it's produced in the largest quantities, because it's the least expensive, it's machinable and easily weldable. It has less than 0.25% weight carbon. The strengthening is accomplished by cold work, and the microstructures consist of ferrite and pearlite constituents. So it's soft and weak, it has outstanding ductility and toughness. So low carbon steels are seen in automobile body components, structural shapes such as I-beams, channel and angle irons, and sheets used in pipeline buildings, bridges and tin cans. So properties of low carbon steels, they usually have a yield strength of around 275 megapascal. The tensile strength is between 415 and 500 MPa. And I think titanium has something like 4,000 MPa, so there's a bit of contrast there. And the ductility is 25%. Yep, 25% elongation. So it elongates by 25% if you stretch it until it snaps. So medium carbon steels. These have a concentration of 0.25 to 0.6. These can be heat treated, unlike the low carbon, so they can be austenized, quenched, and then tempered to improve their mechanical properties. They have a low hardenability, and they're heat treated in very thin sections with very rapid quenching rates. Usually, it's not unusual to add some chromium, nickel, I need to look that. I keep forgetting. Molybdenum. It's called molybdenum. We're going to call that molybdenum. Those improve heat treatment if you add them into medium carbon steels. Now microstructures consist of tempered martensite, which is one of the strong. It's stronger than pearlite, it's stronger than cementite, it's stronger than ferrite. So those are great. They're stronger than low carbon due to heat treatment, but they're not that ductile or tough, because it's what happens when you increase carbon content. So where can you find medium carbon steels? These are usually found in machine parts and high strength structural components, calling for a combination of high strength, wear resistance and toughness. So railway wheels and tracks, gears and crankshafts, usually where you find them. An interesting question I can hear you asking is, why is 1060 steel called 1060 steel? Well, the first two digits indicate the alloy content, and the last two represent the concentration of the alloy. So 1060 steel. For plain carbon steels, the first two digits are 1 and 0, and 60 is the weight percent carbon multiplied by 100. So 1060 steel is a medium carbon steel alloy. So high carbon steels. Oh, no, it's high carbon. My apologies. These things have a 0.60 to 1.4% carbon content. They're the hardest and the strongest. They're not that ductile. They're used in a hardened and tempered condition, so they're wear resistant, hold form very well. They usually combine with chromium, vanadium, tungsten, and molybdenum. I did it. I got it right. So another one that we should have considered slightly earlier are high-strength, low-alloy steels, which contain copper, vanadium, and molybdenum with up to 10% weight. These possess more strength than plain low-carbon steels. They are strengthened by heat treatment, and remember that low-carbon steels can't be strengthened by heat treatment, and they can reach tensile strengths in excess of 480 megapascal. They're ductile, formable, and machinable, but of course, they're going to be more expensive. But if you want something that's sort of like low carbon, but you want to weld it, then you should go for high-strength, low-alloy steels. Stainless steels. These guys are highly resistant to corrosion, hence their name. The predominant alloying element is at least 11% weight of chromium. Corrosion resistance is enhanced by nickel and molybdenum additions. They're divided into 3 classes based on microstructure: martensitic, ferritic, and austenitic. So that's the steels all done. Now let's have a look at the cast irons. These guys have over 2.14% carbon, but industrially between 3 to 4%. They may contain other alloying elements. It's not unusual. It's easily melted and is thus available for casting. Now, most cast irons are very brittle, so the casting process helps significantly. Common types are grey, nodular, white, malleable, and compacted graphite. We're going to look at those. So grey iron consists of carbon and silicon, between 2.5% to 4% carbon, and up to 3% silicon. And the graphite flakes make it look grey, which is surrounded by an alpha ferrite or pearlite matrix. So disadvantages of grey iron, I can speak, is it's weak and brittle in tension as a consequence of the microstructure. Tips of the graphite flakes are sharp and pointed and serve as points of stress concentration when an external stress is applied. Advantages of grey iron, there's a few. The strength and ductility are much higher under compressive loads, but not tensile. Effective in damping vibrational energy, they have a high resistance to wear, they have a low casting shrinkage, their molten state has high fluidity, and they're the least expensive of all metallic materials. All of them. So grey iron is great. You just can't stretch them because they will break. So now ductile or nodular iron. What they do is they add a small amount of magnesium and or cerium to the grey iron before casting, and this produces a distinctly different microstructure and a set of mechanical properties. What happens is that graphite forms, but in terms of sphere-like particles instead of flakes like grey iron. The matrix is pearlite or ferrite. The resulting alloy is ductile or nodular alloy. The casting is stronger and more ductile than grey iron. These guys are used in valves, pump bodies, crankshafts, gears, and other automotive and machine components. Of course, it is just more expensive than grey iron. So white iron and malleable iron. For low silicon cast irons, less than 1% weight silicon, and rapid cooling rates, that's important, most of the carbon exists as cementite instead of graphite. Now the fracture surface of this alloy has a white appearance and is thus termed white cast iron. White iron is extremely hard and unmachinable, so it is usually used in hard and wear-resistant surfaces. So apply your knowledge. We're going to go through a lot of questions to make sure you've got everything, to make sure I've got everything. So the first question is list the classes of steels discussed and briefly describe the properties and typical applications for each. They're right there, but I trust if you want to do well, you'll pause the video. So low carbon steels are relatively soft, highly deformable, machinable, and weldable. As a result, they're used in automobile bodies, structural shapes, pipelines, buildings, bridges, and tin cans. Medium carbon steels are a good combination of strength and toughness. They are thus applied in structure and load-bearing situations such as railway wheels and tracks, gears, crankshafts, and machine parts. Now, high carbon steels are strong, hard, and relatively brittle. These properties can be used in springs, chisels, hammers, knives, and hacksaw blades, essentially springs and tools. Our high-strength alloy steels, HSLA, present a good combination of strength and toughness and an excellent weldability. HSLA steels were essentially developed to replace medium carbon steels with the need of welding, so this alloy is used in large weld structures. That's pretty much the whole point of it. Now, stainless steels are corrosion resistant in a variety of environments and possess a wide range of mechanical properties. As a result, they are extensively used in industries where corrosion is of concern, such as food processing and surgical tools. So question 2. What are the main differences between the steels and cast iron in terms of their compositions, i.e. carbon content, key microstructure features, and melting temperatures? So our steel and cast iron both have carbon and iron with varying amounts of alloying elements, but our cast iron has the higher carbon content and steel has the lower carbon content. Now steel contains ferrite, cementite, and pearlite phases, and cast iron has graphite embedded in ferrite, cementite, and pearlite phases. So cast iron has the graphite. And remember that graphite is what causes grey iron to snap, undergo brittle fracture if you stretch it too much. Now the melting temperature of steel is a lot higher than cast iron as well, so remember that. So question 3. Based on microstructure, briefly explain why grey cast iron is brittle and weak in tension, yet nodular cast iron is ductile with moderate strength. So grey cast iron has a microstructure consisting of graphite flakes embedded in ferrite or pearlite matrix. It is weak and brittle in tension because the sharp tips of the graphite flakes act as points of stress razors, promoting fast crack propagation from graphite flake tips under tensile load. In contrast, in nodular cast iron, graphite takes the spherical forms embedded in ferrite and or pearlite matrix. Such microstructure eliminates the microstructural causes of stress concentration. Thus, nodular ions have mechanical properties close to the lower end of medium carbon steels, which is quite nice, but of course, they're more expensive. So question 4. Is it possible to produce malleable cast iron pieces having large cross-sectional dimensions? Why or why not? So it's not possible to do this because white cast iron is the precursor of malleable iron and a rapid cooling rate is necessary for the formation of white iron, which may not be accomplished at interior regions of thick cross-sections. Alright, cite 3 reasons why ferrous alloys are used so extensively and 3 characteristics of ferrous alloys that limit their utilization. This one is probably one of the most important things to remember, is that ferrous alloys, the steels and cast irons, are used extensively because iron ores exist in abundant quantities. There's an economical extraction, refining and fabrication techniques. They're all well established. The alloys may be tailored to have a wide range of properties, but the limits are that they are susceptible to corrosion, they do have a relatively high density, and they are relatively low in electrical conductivity. So question 6, so because of this electrical conductivity we do have to refer to other metals which aren't as cheap. So list distinctive features, limitations, and applications of the non-ferrous alloys. We didn't go through them, but this is just some extra information for you. Oh, and I didn't write it down. Because we're going to do that, I remember that, because I was going to do this in the next, and I just forgot to delete the slide. Don't worry, I'll do a video on this. So question 7, select from this list the one metal or alloy that is best suited for each of the following applications, and cite at least one reason for your choice. So we've got a block of an internal combustion engine, condensing heat exchanger for steam, jet engine turbofan blades, drill bit, cryogenic, a very low temperature container, and pyrotechnics. Some of these do include non-ferrous alloys. So have a guess, have a think, what do you know? About the Blackbird in the US, that thing has titanium in it, so you'd want to use that. I'll discuss in another video why. So the block of an internal combustion engine should definitely be made of grey cast iron because it is relatively easy to cast, it's wear resistant, and it has a good vibration damping characteristic, and it's relatively inexpensive, so that's what you want to go for. Now the condensing heat exchanger for steam is definitely stainless steel, because it is corrosion resistant and the steam is going to condensate. There's going to be a lot of hydrogen. There's going to be a potential for hydrogen embrittlement there. The jet engine turbofan blades should be made of titanium alloys because they're relatively lightweight and strong and corrosion resistant. Have one drawback is their costs. They are quite expensive. A drill bit, a tool steel would be the best choice for a drill bit because it's very hard and retains its hardness. And at high temperatures, it is wear resistant, thus will retain a sharp cutting edge. Cryogenic, you want to use an aluminium alloy because they do not experience ductile to brittle transitions and remain ductile at very low temperatures. And for pyrotechnics, flares and fireworks, magnesium is the best choice because it ignites easily, just in case you wanted to build some fireworks. It burns readily in the air with a very bright flame. So question 8. Aluminium alloys are mostly used for which of the following reasons? Alright, I know we didn't go through aluminium alloys, but just extra information. So all of them except for their low melting temperature, that they're anodic to most metals. That's actually a bad thing. So non-toxicity, corrosion resistance, high specific strength. That's why we want to use aluminium. So which of the following statements is correct? So the answer is bronze is often used instead of stainless steel for making corrosion-resistant components of complex shapes. Bronze is not an alloy of copper and zinc, that is brass. Brass is not an alloy of copper and tin. I'm pretty sure that is actually bronze. And copper has a high strength to weight ratio. That I don't think is true at all. Question 10. Referring to carbon steels, which of the following statements are correct? And the answer is the last three. Train wheels are not made of high carbon steels because remember they're quite brittle. Even though they are strong, they are very brittle. So you do not want to use them on train wheels because they will snap in half and everyone on the train is going to die. So this is why we use medium carbon steels, because they're great for structural components. High combined strength and toughness. Drill bits are also often made of high carbon steels, that is correct. The strength and toughness of carbon steels increase with increasing amount of carbon. That is also correct. Strength and toughness. Don't get toughness confused with hardness. Question 11. Aluminium is one of the most recyclable metals because it has a low melting temperature. It makes it easy to just chuck it back in the furnace and create whatever you want. So which of the following elements is primarily responsible for the stainlessness of stainless steels? It is chromium. Referring to cast irons, which of the following statements are correct? Malleable cast irons, rather than steels, are suitable for making a component with thin walls. And cast irons have a much lower melting temperature than steels, that is right. And that is it. So hopefully you have a basic understanding of ferrous materials, and I'm just going to go back to that diagram at the beginning. And you've also learned a little bit about the non-ferrous alloys as well, which is great knowledge to have. And yeah, so there you go. So we've covered all of the steels, so low alloy steels, which don't have a lot of carbon in comparison to our cast iron. So our high alloy is our tool and our stainless steels, which have a lot more carbon. They've got a lot of other things. We also had a look at low carbon, which has high strength low alloy in it, and this makes it great for wooding things together. We've just got plain, which is carbon and iron. There will be some residual elements in there, but mainly it's just iron and carbon. Medium carbon, it's heat treatable, unlike low carbon, which has to be cold work, and high carbon, which is great. It's usually used in tools because it's slightly brittle. Alright, that's it. Thanks for watching.